Okay. Hi, everybody. It's a real pleasure to have with us Mark Lewis, who's been to this seminar before, perhaps with a different name, but we are happy to have him back again. Mark graduated from the University of Victoria, did a PhD from Oxford, did a short postdoc at the University of Washington, then was at Utah for a while as faculty member, came back to Canada, Alberta, as a Canada Research Chair, and now is the Kennedy Chair. James and Betty Kennedy, someone Kennedy Chair at the University of Victoria, has come back full circle. He has done a lot of fascinating work on various aspects of applying differential equations and mathematics to biological sciences, including generally with a focus on spatial phenomena, if I can have this right. So over to you, Mark, and we're looking forward to hearing about how a single equation can help solve three paradoxes in spatial ecology.
Great. Oh, thank you, Suresh. It's really nice to spend some time talking to you, um, and to be part of the CAMBAM seminar. Thank you for having me. I want to make a acknowledgement that this is the area that I live and work in, near the University of Victoria in southern Vancouver Island. And it's the traditional territory of the Lekwungen people, where the University of Victoria stands, and also the Songhees, Esquimalt, Wasanik people, who have a historical relationship that continues to the land to this day. So I'm interested in how things move, and in the slide here, you should be able to see a simulation of a random walk. There's particles undergoing Brownian motion. They all started at the origin, and now they're spreading out. And when they hit the edge, they stop moving. And so we may be interested in the probability density function that describes where we might find one of these particles at a particular time. We also might be interested in how long it would take, on average, to hit a target, such as the edge of the domain. And these two ideas are going to feature strongly in the talk today. But in fact, today, I'm going to be talking about predators and prey and using some of these ideas. And I'm going to mainly focus on wolves. These are animals I've worked on studying for about 30 years. And there's three paradoxes I want to bring up from a biological perspective. Wolves appear to be attracted to roads and related linear features in the environment that are man-made. And but it's very clear that they're more likely to die when they're on these roads. And so we might ask, why are they using these roads? Another question is a little bit more complicated with respect to interactions between wolf packs. There is some very good evidence that wolves maintain buffer zones between wolf packs, which act as prey reservoirs. And these are accessible to both packs simultaneously. And from a perspective of fitness, you might wonder, why would wolves do that if by maintaining a buffer zone, they're providing prey for an adjacent pack? The third paradox is what I would call the path less traveled paradox. Data show that wolves preferentially travel to places they haven't been to recently. Even if they were recently preying on some species that are at high density, they'll often go to places where they haven't been and they're not aware of what the prey density is. And so we might ask, why would they do that? Why wouldn't they just go back to places they know are good for resources? And so I'm going to talk about these three questions and bring them together with one equation, and it's the Fokker-Planck equation. It's quite famous in physics and math biology, and it describes the dynamics of spatial movement of individuals over time. And so this is a study organism in Banff National Park, close to where I used to live in Alberta, Canis lupus. But before we talk about the issue with the three paradoxes with wolves, I'm going to talk about a very famous study on red fox movement. And this will help us to build a foundation of tools that we can use. And this is a picture of the red fox. And there's a very famous data set that goes back to the late 1960s in this creek ecosystem. It's in Minnesota, and radio telemetry was new, and they were put a tracker on a fox, and they followed it for 30 days, and they got its location every 10 minutes, and this is the pattern that was observed. And so if we try to analyze how the animal is moving, we can break down the movement path into different components. One component is the step length distribution. And so we have a probability density for the step length here, and the distance is shown on the horizontal axis. It appears that the animal isn't moving like the simulations that we had originally been looking at. It's not wandering off very far. In fact, it seems to be orienting itself in its movement pattern back towards the den site, which is this triangle in the middle here. And so we can think of an animal at the point Y moving to the point X, and then the den site is denoted by the H. And so we may ask how the movement direction is relative to the movement moving straight back to the den site. And so if we plot the turning angle relative to the den site, we see there's a distribution. So there's a focus towards the den site. And so if we put these two things together, and if we make the assumption that people often do, but may not always be correct, that the step length distribution and turning angle distribution are independent, then we can describe probability density associated with moving from Y to X by multiplying the step length distribution by the turning angle distribution. And this is what people often do. And so we can model how the animal would move over time. And here, tau is a time step, and U is a probability density function, describing where an animal is in space X as a function of time. And this master equation, shown on the first line, updates the probability density function over a small time interval. We have this movement kernel that we saw on the previous slide, and of course, the movement kernel depends on the time step. So there's a tau, and then we have the space use of the animal at time t, and then we move forward one time step with this master equation. And so one thing that people have done over the years is rather than work with the master equation, they approximate it. And this is goes back a long way in probability theory, and it was popularized in mathematical ecology by Akira Okubo in the 80s. And so the idea here is that we approximate the master equation with a partial differential equation, and we're really approximating it in terms of the moments of the kernel F. And so the first moment will give rise to a bias term, C, that then creates an advection term. And the second moment gives rise to a variance type term that describes the diffusion. And in the full depiction here, the diffusion depends on the location X, and it can be different in different directions. And so we have a Dij. And these moments are given at the bottom here. And so we have the possibility of anisotropic diffusion and advection. And so if we're interested in the probability density function over time, we often use this Fokker-Planck equation. And so that's the movement kernel. And then we see the movement kernel appear in these moments as well. Okay, so if we just apply this approach to the red fox movement, we have our movement kernel here in the bottom left, and we have our time step, which is given here. And then it turns out that our advection vector is a vector pointing towards the den site. So that's what the minus x over norm x is there. And then the gamma is the speed of movement back towards the den site. And then the diffusion is isotropic in this case, and we can calculate what it is. So we can calculate these from the data. Okay. So with that under our belts, we want to now talk about these more subtle problems. And the first is this road use paradox. If you fly over the foothills of Western Alberta in the wintertime, this is what you'll see. So you can see the linear features very easily because of the snow. And wolves use these. The ones we're looking at here are not primarily roads. They're primarily coming from oil and gas exploration. And so I was fortunate to be involved in a project where wolves were radio collared and tracked every 5 minutes, and their movement behavior relative to these roads was assessed. So these are the anthropogenic linear features in Alberta. And we have 3 different kinds. We have roads, and then we have these pipelines, which are also quite wide, and then seismic lines, which are very common, and they're used for oil and gas exploration. We can see the roads in the green on the left and the pipelines in teal, and then the seismic lines, you can see there's very many of those in the yellow. And so if you were to pick a location in the foothills of the Rockies, you'd typically be within a kilometer or perhaps even less of a seismic line. Okay, so now we'll go back to the question, why are wolves attracted to roads and related linear features, even though it might mean that they'd have a higher chance of dying? It turns out that the yearly survival of wolves in Alberta is quite low. It's about 50% or so. And the top 3 sources of mortality are anthropogenic, from trapping, hunting, and highways. And these all increase strongly near linear features. However, they're still used widely for traveling, which is a bit of a paradox. And then one question is, could this improve hunting efficiency? And so the idea is perhaps when we go to the grocery store, we might get on the freeway and drive to get to the grocery store quicker. And if perhaps the wolves are doing the same thing with these linear features and getting to their prey faster. So we're going to start by assessing how linear features could make wolves more efficient predators. And the idea here we use is that of first passage time. And the first passage time is a random variable, as we saw in our initial simulation of the length of time it took to hit the edge of the domain. But we're interested in this case of the mean first passage time. So averaged over all the possible realizations of the stochastic process. And this is the average time for a random walker starting at a site starting at X to reach a site for the first time. And in our case, the sites are going to be the prey. And so we're going to try to determine how long it takes wolves to find prey without linear features and with linear features. And if we deal with a spatially heterogeneous environment of the sort that we saw from the photographs, we need to include the possibility of anisotropy. This is the Fokker-Planck equation that we've seen before. And this describes the probability density function for the location of the animal. There's a related equation that will describe the mean first passage time, and it involves the C and D terms, and it looks like this. So I won't derive it here, but it's an elliptic equation, and we have the advection term given here and the diffusion terms given here. And then the boundary conditions are absorbing at the target site. So if you start at the target site, then your mean first passage time is 0. And then typically they're reflecting on the domain boundary. And so what we're going to be interested in doing now is solving this mean first passage time in a spatially heterogeneous environment with linear features. And so, again, this is a reminder of the kind of environment we're dealing with here. And so what we ended up doing was we kind of broke the entire region we were interested in into three different types of areas. One is far away from seismic lines, where we assumed that the motion was more or less random. And then there's when one is near a seismic line, and we allowed for animals to move anisotropically relative to the seismic lines, plus they could be attracted to the seismic line or repelled from the seismic line with this C of x here in the second equation. And then once we're on the seismic line, we assume that animals are moving, but they're moving in an anisotropic way because they're moving quicker along the linear feature than they are transversely. And so we can estimate these coefficients, the C's and D's, and this comes from these wolves that were tracked. And this is what we see here. And so we're interested in the step length and the turning angle. Now the turning angle isn't relative to the den site as it was before, it's relative to the seismic line itself. And so the step length is shown in the top here. This is for one of the wolves, okay? This is wolf number 233. We had a number of wolves that were tracked. I'm just showing this one for interest. The step length is larger on the seismic line than near or off. On the seismic line, the movement is along the seismic line. And so this is the angle relative to the perpendicular direction to the seismic line. So we're seeing peaks in the forward and reverse directions. However, near the seismic line, the wolves are attracted, and we see this single hump shape here. Whereas off the seismic line, the angle seems to be more or less uniform. And so we can put this all into a numerical simulation where we actually take a real piece of environment with the seismic lines shown here, and we put in prey, and then we solve the system of equations you saw on the previous slide numerically using what's called COMSOL. And so here the targets are these black dots, which in this case are randomly located. We tried other possibilities like clumping them, but I'm just going to show you the case where the prey are random in space. And then this mean first passage time would be 0 at the prey item itself. And so this is what a numerical solution would look like, where we see the dots, the mean first passage time is 0, and this is in hours. And so in the bottom left, where the individual starts a long way away from a prey item, it might take them 160 hours, say, to find a prey item, several days, where if they start closer, it would take them typically less than a day. And so we can do these numerical simulations for a variety of different scenarios, and we can change the densities of the seismic lines, and then try to understand how long it takes for the predators to find the prey. And so that's a good start, but what we're really interested in is how efficient are these predators as hunters? And is this efficiency increased in the presence of seismic lines? And for this, we use what's called a functional response. And here, E is the encounter rate, and it's a function of the prey density N and the seismic line density S. And so we're going to use this approach here, and this is called a type 2 functional response. So it's a saturating function. And T sub H is called the handling time. And so when wolves encounter a prey item, they sometimes don't hunt for several days as they consume the prey item and digest it and so on. And so this comes into the functional response. And so we're interested in how quickly the wolves are finding their prey as a function of the seismic line density, but of course the prey density comes in here as well. And so what we're really interested in is the increased efficiency of hunting in the functional response in the presence of seismic lines where S is positive relative to if there were no seismic lines, S equals 0. So here E is the encounter rate and T is the handling time, and E is 1 over the first passage time. And so from the mean first passage time, we can invert that to get a rate. And so when we plot the ratio of functional responses shown on the vertical axis here as a function of prey density, we can do this for different densities of linear features. And so these linear feature densities are the S's from the previous slide, and the prey densities are the N's. Okay, and so what we've done is we've looked at this ratio of how quickly you're consuming prey in the presence of seismic lines relative to no seismic lines for different cases. And so the base case here is where seismic line density is 0, and so the ratio is 1. And then the solid line here is where the seismic line density is 3.1 kilometers per kilometer squared, which is the typical density found in the area we were looking at. And then we also upped it to a higher level, which is likely to occur under increasing industrialization, which is 7.6 kilometers per kilometer squared. And so what you see is kind of interesting. When the prey density is high, the seismic lines don't really make the predators much more efficient hunters, because the handling time dominates. But when the prey density is low, they would be 20% more efficient, or under increased industrialization, about 40% more efficient as hunters. And so the idea here is that when prey densities are low, these seismic lines can mean that they're predated on much more quickly, because the predator is needing to find them, and they're rare. And this is the case for some predators such as caribou that are found in Alberta, where there are very few of them, and the wolves are predating on them. Okay, so that's kind of our understanding of the paradox here. They're more likely to die on these linear features, but they're more likely to become more efficient predators. Yeah, so at low prey densities, wolves consume more prey in landscapes with linear features, and this is a reason to attract them, the linear features. I'm going to move on to the second question here, which is a buffer zone paradox. Why do wolves maintain stable buffer zones for prey, even though they may be only saving prey for the neighboring pack? And so we want a model for territorial interactions between wolves. They forage by moving around their territories while searching for prey. And there's a lot of scent marking, which produces some spatial patterns. And existing scent marks cause some kind of positive feedback mechanism that increases scent marking. And their movement itself changes in response to scent marks. And when all these dynamics play with each other, then there sometimes are these buffer zones that appear through the communication through scent mark and movement interactions. And so these are what the scent marks look like in different colors. There is a central pack here in the middle. And then fortunately for us, the scent marks are in different colors. And this map was reconstructed by a PhD student many years ago doing snow tracking and looking at scent marks. And you can see the edge of the bowl here where the territories come together. At the same time, there is some very good evidence that where the deer are found in, at least in northeastern Minnesota, is often between the wolf territories. And so there were two studies. One was tracking wolves, and the different dots show the locations of wolves from different packs over a season. And then at the same time, there was a deer radio tracking study, which shows the locations of the deer with the green dots. And you'll notice that the green dots are right at the edges of the wolf territories and between the wolf territories. And so the deer density appears to be highest at the periphery of the territory and in the buffer zone. The red areas are these yards where the deer congregate in the winter. And these are also near the edges of the territories or between the territories, except maybe over on the left there, these deer could be in trouble. Okay, so you might ask, why do wolves maintain these stable buffer zones for prey, at least in this part of the world in Minnesota, even though they may be only saving prey for the neighboring packs? And so we'll start with a mechanistic model for how buffer zones can form. And then we'll allow the packs to play a game where they're trying to maximize fitness. And so we'll use the Fokker-Planck equation as their basis, but then we'll kind of shift to a game environment. And we'll consider the case where there's some kind of intrinsic randomness in the behavior of the wolves. And we're going to couple that to a sufficiently strong penalty for inter-pack altercations. And we'll show that that may be sufficient to cause these buffer zones with the prey. And we'll think about that as what's called a Nash equilibrium. And so we can modify our Fokker-Planck equation here to allow itself to depend on auxiliary variables P. These are typically environmental variables. And so the advection speed can depend on the environmental variables, and the diffusion coefficient can as well. And in our case, we're going to consider scent mark. So it's appropriately named. And so we're going to allow our underlying environmental variables to have their own dynamics. And so the basic model goes back quite a few years. And we have the density from pack 1 is U, the density from pack 2 is V, and U is producing scent marks P, and V is producing scent marks Q. And so where U is higher, P will be higher, but V will be avoiding P and U will be avoiding Q. And this can cause the territories to form through avoidance of foreign scent marks. And so the simplest form of the equation is shown here, where we have a version of the Fokker-Planck equation in the first two equations for pack 1 and for pack 2. And then there's an advection term, which describes avoidance. And we're thinking of a den on the left-hand side for pack 1. And then there's random motion. And then there is avoidance via advection for pack 2. And each of these terms for avoidance depend on the scent mark density from the other pack. And so U produces P, but V avoids P, and V produces Q, but U avoids Q. And then the scent marks themselves can have their own dynamics. There's deposition, and then there's some kind of positive feedback overmarking in the presence of foreign scent marks. And then there's decay. And so this describes a full problem. We need initial and boundary conditions. And then we can look for equilibria to this, and these correspond to spatial territories. And so we can mathematically analyze existence and uniqueness of the equilibria. The basic idea behind this is that we, if we look at the first two equations and we set the time derivative to 0, then we can integrate them once, and because we have derivatives on the right-hand side that can be integrated once. And so then we can also solve the last two equations by setting their derivatives to 0. And we solve them for Q as a function of U and V, and P as a function of U and V. And then we substitute in the steady state solution. And we get these two coupled ordinary differential equations that describe the rate at which the space use density drops off with distance as a function of this avoidance term here. And then we have, it turns out it's not an initial value problem. it's a problem with an integral because we are conserving the total density of both packs. And so these are the kinds of equilibrium solutions that we get. So this is pack 1, this is pack 2. The cent mark for pack 1 is shown there, and the cent mark for pack 2 is shown there. And so you see you're getting these edges of the bowls that emerge spontaneously through this pattern formation process where there's this positive feedback mechanism where pack 1 is cent marking, pack 2 is over marking, and then this is causing them both to avoid the region and produce a buffer zone in the middle. And so in the case of the buffer zone, the lower density in the middle provides a refuge for the deer. And so we put a deer model into this that assumes the deer are being born in the spring and predated on through the year. And then we look at the deer density in the spring versus the winter. And this is the solution we get here. So this is the underlying mechanism that we can kind of see at play here. And when we fit this to data, we can, this is actually not wolf data, this is coyote data, work with Paul Moorcroft and Bob Crabtree. We can estimate the parameters and here the den sites are shown with the triangles, and the contours are showing level sets for the expected space use density. And for the middle pack then, this is all the edges of the bowl that it would be seeing in terms of the foreign cent mark level. And these foreign cent marks are driving it back to the middle region here. That peak right over here is right where these 3 packs are, oops, 3 packs are interacting. So there's a very heightened level of cent marks there. And we can relate this back to the random walk if we want. And so this is sort of where we started with, but now our random walk has a step length distribution and a turning angle distribution. And the turning angle distribution also depends on the density of the cent mark here. And so this is the sort of the bias in the random walk that is associated with moving back towards the territory in the middle there. So we're going to take all this machinery and then we're going to go back to this question. Why would we expect to see these patterns in nature? Why wouldn't the wolves modulate their parameters somehow so as to raid these buffer zones and consume the deer and then kind of increase their own fitness? And so we can think about these wolves that are essentially obeying the Fokker-Planck equation as playing a game. And the game is to modulate the parameters in the equation so as to try to maximize their fitness. And so the question is, why don't the adjacent packs enter the buffer zones and consume the prey? And how do they persist as stable ecological entities? And so the theory that we use here is of differential games. And so we might say, how should a pack modify its movement behavior so as to maximize its fitness? And so we can think about how we change our bias and our random motion in our random walk process so as to try to optimize fitness. And if we look at a simple case like the one given here, we haven't got the cent marks in here. We've just got some spatial variation in the location here. So the bias term can be modulated according to the location in space. We might look for an equilibrium solution to that. And then we have these 2 coupled ordinary differential equations, which are non-autonomous because the bias term, how quickly you move back towards your den site, depends on where you are. And you're trying to maybe think about how you might choose this C function so as to try to maximize your fitness. And so this is called the differential game. If we have a something we're trying to maximize here. And so what we're trying to maximize here is a term we'll put on the next slide, which is the intrinsic growth rate of the pack. So how much food is it going to essentially accumulate over a year, modulated by the probability of perhaps dying. That's what this R sub U is. And so the idea is that it wants to choose this beta term shown in the red box here, so as to try to maximize its fitness. At the same time, the other pack is trying to choose its beta so as to try to maximize its fitness. And so this becomes a game, right? Because what you do depends on what the other pack does, and vice versa. Okay, so we've gone from the Fokker-Planck equation now to game theory. And so finally, we want an expression for the fitness, and I've got it in the geometric term here. There's some kind of survivorship, and since natural mortality, it turns out that the wolf packs are quite hostile. So if they run into each other, they're more likely to die, and that's what this shows. And then there's the offspring produced, which is dependent on the deer density, which in turn depends on the space use by both packs. And again, the U and the V that come in here now depend on this choice that they have for the bias term. And so the idea is for a Nash equilibrium, we would have rules for these betas for this avoidance term that are uninvadable, in the sense that a pack digressing from these rules will not increase its fitness. And for fitness, we're just using the log of the geometric fitness here. And pack 1 is trying to maximize RU, and pack 2 is trying to maximize RV. Okay, so that's the setup for this. I like it because it takes this Fokker-Planck equation, and then it sort of moves to this sort of game theory perspective. And I'll just say the results in words here. The two packs play a game where each pack is asked to choose the space use so as to maximize its fitness. And in the simplest case, the game involves no constraints on movement behavior. And in this case, the space is partitioned into two halves and no buffer zone. So the wolves use all the space, and their territory is just a butt, and then they drop off precipitously. And this is what you see, say with most countries, right? You just have a boundary. And a more complex game involves constraints on the movement rules. So the values that the ratio of C over D can be. In particular, we can assume perhaps that there's always a random or unpredictable component to motion, and that the maximum bias is limited. And so what this means is if you got to the edge of your territory, maybe there's some randomness about what you're going to do. You don't know necessarily if you're going to go directly back into your territory. You may see a deer, and you may infringe on the buffer zone and make an entry there. And so this uncertainty makes a very big difference in the game. And indeed, if we assume that there is this uncertainty, which is given by D being greater than D min, and C not exceeding C max, the Nash equilibria arises with a buffer zone in there, providing there is a sufficiently large penalty for antagonistic interactions with neighboring packs. Okay, so this term alpha here then means that if you're running into an individual from the adjacent pack, you're more likely to die. And the buffer zone provides a refuge for the deer. And so this is a kind of an explanation why these buffer zones might persist for long times. It's because the behavior is inherently uncertain at the edges of the territories, and therefore you sort of better keep away, because who knows, something bad could happen. And we believe that this is actually what's happening. And so we can think about this penalty for overlap here, alpha on the vertical axis, and the unpredictability of the movement here. And we can actually compare with different species, which is sort of interesting. And so if there's high penalty, high alpha, and a high predictability, then we get this partitioning of space. Whereas if there is little penalty for overlap, alpha is low, and unpredictable movement, you'd see overlap between territories. Whereas if there's high penalty for overlap and unpredictability of movement, we think this is the wolf situation, where you get these buffer zones. And so what I'm showing here is the calculated Nash equilibria from these differential games. And when we think about species, this space partitioning is seen particularly with things like badgers, where they have very clearly marked territories with these trails that show exactly where the edges of the territories are, and they use the space right up to the trail. In the case with territorial overlap, the coyote situation actually has quite a bit of territorial overlap, whereas the case with this high penalty for overlap and unpredictability is best described by the wolf territories. And so we think we can kind of understand how these different situations arise. There are buffer zones in human populations. This is a buffer zone between North Korea and South Korea, shown here. It was formed by an armistice in the 1950s, and it's been maintained for a long time. And perhaps surprisingly, it's also a thriving hotspot for biodiversity. And so there are species found here that are not found elsewhere. And it houses quite a number of endangered species. Okay, in the last few minutes, I'm going to talk about the last paradox that also refers to wolves. And this is couched in the question, why do wolves preferentially travel to places they haven't been to recently, even if it means fewer prey? And so this was originally inspired by some work in the forest in Poland. And wolves from adjacent packs were being tracked day by day. And this is one wolf from each adjacent pack. This is their movement in the first day. This is the movement in the second day. This is the movement in the third day. And you can see there's a very strong sense that they're not going back over their paths very much. They're exploring new regions. And so we wanted to think about this. And so it's generally true that wolves preferentially avoid places they've been to recently. So it could be that they're patrolling by collecting information. We think about the possibility that this information could increase since the last time they were there. And so you're more likely, if you're harvesting information, you wait for the information to grow, and then you go back and harvest it and see what happened. Alternatively, they could choose not to return to places they've recently hunted due to prey vigilance. So if you've hunted in a region, maybe the prey are vigilant and you want to give them time to recover. And so we model this using a kind of a random walk process with memory. And so the idea is that kind of shown in the simulation here, if you have an animal moving around a region, say its territory, you can keep track of the time since last visit. And so here the red colors show a long time since last visit, and the lighter colors show a place that the animal's recently been. So when you look back at the track, you can see the time since last visit along the track is quite low, but there are regions that are it hasn't been to for a while that are shown in the red there. And so if you think of an animal moving, maybe it's preferentially going to go to one of those red areas just to see what's going on, especially if it's a territorial animal and likes to patrol this territory. And so here we're stepping back from the Fokker-Planck equation a little bit and looking at the underlying stochastic process. And this is the location of the animal at the next time step. It's given by the same f function. This is the probability density function with respect to its new location x, given that it was at xt at time t. Okay, so xt is the stochastic process that's describing what's going on there. And the usual way that biologists model this function is to, again, multiply the step length distribution by some weighting function. But this weighting function, rather than looking at the turning angle necessarily, looks at how some regions may be preferable to other regions. And so maybe the weighting function would put higher weight on the red region than the light colored region. And it's a normalizing factor on the bottom here. So they refer to this as a step selection function. And so the idea here is that this argument to the weighting function can depend on these environmental covariates in some way, perhaps in a form of a generalized linear model. And one of these entries could be the time since last visit. It could also involve the prey density, and it could involve other things too that are shown a little bit lighter here. I'm just going to focus on these first two things here. And so, so the idea is if we have a model like this, we can actually fit it to data and estimate the parameters, the betas in this function here, and see if they're preferentially choosing places where they haven't been. And so here, the quest is to actually see if they're using this time since last visit rule. But to see what's going on, we can just think about simulating a random walk for a wolf under different models. And so in the first case, it's just undergoing a simple random walk. The resource density is shown in red, but it's not responding to it. If it were to respond to the resource density, then the weighting associated with the prey would have a positive coefficient beta, and then it would localize on the prey. On the other hand, if it was trying to maximize the time since last visit, it would have a path like this that looks a little bit more uniform over a period of time. So it's getting to all the different locations to see what's going on. But in reality, it could be both, which is what we see here. Okay, so we fitted these models, including time since last visit and prey density, and some other terms to wolf radio tracking data from the University of Alberta using maximum likelihood. And the idea was to try to deduce, to back calculate the behavioral rules that the wolves were using to make their movement decisions. And so the results supported that it was, they were using the time since last visit to modulate their movement behavior, to make it more like patrolling behavior. And there was also a strong interaction between the time since last visit and the distance to the edge of the territory, as well as the time since last visit and the prey resource density. So the first of these, time since last visit and the distance to the edge of the territory, could be best understood in terms of patrolling. So maybe the value of going back to a location at the edge of your territory is higher than in the middle if you haven't been there for a while, because that's the edge of your territory. And the time since last visit and the prey resource density can be understood in terms of this sort of idea of landscape of fear. And so the idea is that if you've recently been in an area, maybe you won't go back to it right away because the deer are onto you, and you won't return immediately. You go back to an area you haven't been to for a while. And so that's what this last bullet says. We picked up the signal of patrolling territorial boundaries plus this landscape of fear model. And so this is just one of the, this is the real data from particular wolf. Prey density is shown, normalized prey density is shown in color, and the path is shown here. And okay, so we're getting close to the end of the talk. What I'm particularly interested in now is putting learning in movement models, and I believe this is a new frontier in movement ecology. And it becomes rather complicated, though, because individuals are responding to their environment, but also their what they learn from their environment. And so there's these intriguing experiments that happen when animals are released into new locations, like in rewilding. And so we worked on, say, panda bears being released from the zoo into a natural environment, and then we see how they move over time. And there's some initial exploration stage, and then they learn, and then they kind of modify their behavior in the long run. And so I think this is a fascinating modeling area. In summary, we started off with a kind of a classical simple model for the fox movement. We started to look at the behavior with respect to first passage time and predation efficiency, and we could analyze this. And then we looked at this territorial model and tried to understand the emergence of these buffer zones. And then we moved to the idea that we would have the time since last visit that might modulate movement behavior. And this is the kind of data we had there. So thank you very much for listening, and I'm happy to answer questions.
Great. Thank you very much. Questions? You can unmute yourself and ask, or raise your hand, or type in the chat. All good. While we are waiting, I'll let me ask.
Sure.
So for me, this is an entirely new field, right? So I'm thinking very qualitatively, and these buffer zones are fascinating. So I guess there's more variables that you can, of course, include, right? So one that I was thinking of was the relative strength of each pack. So in other words, if a pack is stronger, the buffer zone should migrate effectively. And also the other one would be prey density. If the prey density is low, then the buffer zone should be overrun because you have more of a reason to go hunt there. Is either of these valid as an intuition?
Yeah, there is a scaling law that relates the sizes of the territories to the sizes of the packs. And so it's like a nonlinear scaling law that is consistent with what you were saying. With respect to the buffer zones, they're fascinating entities, and the area that I mentioned, which is in northeastern Minnesota, has had these buffer zones for many decades, and they're very stable. But in a lot of other areas, these buffer zones don't exist. And so they're these fascinating entities that are not, in some sense, generic. And I think it requires this sort of delicate balance between um, the um, the parameters associated with the prey density and the wolf pack sizes and so on and so forth. And I think you're quite right that they would change under different scenarios. Yeah.
Yeah, is there potentially a role for like finding out something like cultural learning, as in don't go there. So even if the pack strength becomes low for a while, there's memory that says we don't go there.
Mm-hmm. Mm-hmm. Yeah, yeah. This is really a interesting thing you bring up. Um, I mean, anyone who has a dog realizes that dogs and wolves are quite sophisticated animals, and so you may even ask, why could you model a wolf with a Fokker-Planck equation? But my answer to that would be that there are approximations that describe sort of average behavior over long terms, and so a particular individual may not be obeying the rules that you think it should be, but in the long term, hopefully the model brings out some general principles that are still applicable.
But yeah,
And yeah. Mm-hmm.
no, I was just wondering more that for a while you could fake it, right? Like if you have been a strong pack for a little while, then you can maintain the buffer zone. But so even if your strength goes
Mm-hmm.
down because the other side has not had a chance to discover it, or even they've discovered they're reluctant to. I was just wondering if you tease out this element of cultural learning or
Mm-hmm.
transmitted behavior, it becomes interesting to biologists, right? As a
Mm-hmm.
conceptual term, right? Because there's
Yeah.
always this notion of is there learning or not that is
Mm-hmm.
transmitted across generations. That's what I was trying to go after.
That is very interesting. Yeah. Yeah. On the same vein, we actually had a situation with the coyote populations where these mechanistic models can predict what happens when a pack is removed,
Yeah.
and so we did this in Yellowstone, where a pack coyote pack died, and we predicted what the other packs would do, and then we could compare the data of how these pack territories rearranged
Ah, so
relative to the removal. as predicted by the model and as seen by the data. And in actual fact, they moved in very quickly.
Okay. Okay.
So yeah.
So they are really
Yeah,
fast.
Andre, I see you have your hand up.
Hey, Mark.
Hi,
Thanks for your talk. Um,
sure.
one thing, do the prey distribute themselves away from the linear features? Do they learn anything about the ecosystem?
Yeah, so they don't appear to.
Okay.
Yeah, there's not as much evidence at all that they are either attracted to or repelled from linear features as there is for wolves.
Okay. In the analysis for the buffer zones, your equations seem to be in 1D, so the packs can kind of go right through each other. But do you expect, or have you done the consideration of a 2D, in which case, things can move around without interacting so much?
Yeah, that's a really great question. We have numerically simulated um, the 2D situation uh, with respect to the formation of the buffer zones. And we see qualitatively similar behavior. We haven't formulated the game in 2D,
Right.
which could be a very interesting but somewhat difficult thing to do.
Right. If I can ask another one, Soresh.
Yeah, yeah, of
Sure.
course.
So we've been studying, the formation of cognitive maps in mice and fish, like from the neuroscience perspective, and they do fascinating things. Now that, so they're, but the goal is really to find food and to exploit that food. It's not so much an exploration. At the beginning, it's an exploration, but it turns into an exploitation that kind of refines the random walk and the way they're building their heat maps, let's say of their paths, kind of
Hmm.
builds from the target where the food is and moves back. That seems to be how they learn,
Hmm.
and there's adaptation going on in the neural circuits to wire this. So this is stuff we've been working on for the last few years. So I was interested in what's your perspective on what the animals are doing, what the, let's say, the wolves are doing with respect to the deer. Are they really playing a game of hide and go seek? They're not exploiting so much or exploring. They're kind of doing a real mix of the two, but with some kind of waiting time before they go back to the place. Like they,
Hmm.
so they
Hmm.
have this time scale of revisiting after a certain amount of time. So what's your perspective on what the strategy is? Is it
Yeah,
exploitation, exploration?
this is fascinating. I would love to talk to you more about the
Yeah,
cognitive map part. It ties in with this whole learning perspective on animal movement. Um, I think with the wolves, it's a little bit complicated. So I mean, there's really two key elements that they need to take care of. One is maintaining the hunting efficiency, and the other is territorial defense and scent marking.
right.
And so they're competing with their neighbors at the same time as wanting to maximize their prey input. And so I believe that the time since last visit plays a role in both of these in different ways.
Mm,
And so the time since last visit means that if there's an area that the wolves have not been to, that's near the edge of their territory, uh, they they haven't been there for a while. They should go there. Uh, that's also what the data show in terms of this term in the model, that they will revisit places they haven't been to for a while, especially if it's near the edge of the territory. With
mm,
respect to the deer, there's been a lot in ecological literature about this idea of a landscape of fear, and so the idea is that the predator like a wolf on ungulates will induce a very strong behavioral response where the with anti-predator vigilance and things like that, and change the feeding habits and the reproduction habits and all these kinds of different things as they adapt to their predators. And so the wolf is trying to manage that as well. And so that means they don't go back immediately to places where they have been hunting, and they wait for a little bit longer before they go back, typically up to even a couple of weeks. And so
Wow.
the idea is that then that allows the deer to re-equilibrate away from the anti-predator vigilance.
It's amazing. They can figure this out.
Yeah. Yeah, and it's amazing that you know, with sufficiently many wolves, like we had quite a number that we were tracking there, we can detect the signal of these different elements and kind of try to tell a story about it. We think it's true, but you know, there may be other explanations as well.
Yeah. Great, thanks.
There's a question in the chat. Terry, do you want to ask, or should I ask for you? The question is there a clear relationship between the step size distribution and the linear features?
Yes, actually, maybe I'll go back to that. Yeah, I don't have the step size distribution in the slides, but I have the average step length. And I have to go back a little ways here. There may be a more efficient way of doing this. Here we are. Yeah, so yeah, this is a picture with the linear features in the bottom left and the environment. And so on the linear feature, the turning angle is such that the animals are moving, you know, in the parallel direction to the linear feature, and the step length is considerably longer. So in the top right, you'll see this Wolf 233, and for step length, that's a vertical axis. The location is the horizontal axis. If you're on the linear feature, then your step length is longer. Yeah. Yeah.
Great. Any more questions?
So yeah, I
Go
would
ahead.
kind of, you know, we have thought about trying to modify these equations to include kind of more correlations in the direction, because on the linear features, you know, the wolves aren't really diffusing along the linear features. There's a very strong correlation in step length distribution. And there's some intriguing new work by Thomas Hillen and collaborators on these hyperbolic models for animal movement, where they can also calculate the first passage time. And so we'd like to extend it in that direction.
Great. More questions?
Curious, Mark, thank you for a really wonderful talk. I'm curious about wolf learning as well, and you've just told us what they can learn with respect to their prey, but do we know how aware they are of the dangers of like hunting and other things? Like how do we know to what extent wolves know that this is dangerous for them?
Yeah. Yeah, there's a lot of work to be done there. Yeah. Yeah, we can sort of work from two ends, and so the middle part of the talk sort of worked from the idea that interpack altercations were dangerous, and we had this alpha term, and I could actually calculate the value for alpha based on historical records for wolf movement in Minnesota. So somewhere not in the talk, I have an estimate for what that is. So how much does overlap affect the fitness of individuals? So that's at one end, kind of looking at long time periods and statistical averages over what happens. And then there's the other end of the spectrum, which is more related to the last part of the talk, which is following an individual as it executes a random walk, and then trying to infer the rules that may be governing that random walk. And there, of course, we don't know what they know or what they're thinking. But we can sort of measure in some sense what they do with these the weighting function that ascribes different weights to different kinds of spatial locations that are associated with not having been there or something else. And it would be great to bring these closer together. It would be fascinating to do so.
Okay, yeah, thanks.
Cool. So there are no more questions. One more time, thank you very much, Mark. And it was a great talk. And yeah,
My
Looking forward
pleasure.
to-
Yeah.
Yes, great. Bye.
Thank you for
See you,
having me.
everybody.
Okay.
Thanks for coming.